A developer types a single line of code and triggers an action on a server sitting 3,000 miles away. To the person at the keyboard, the process is seamless. They ask for data, and the data appears. This seamless experience is an engineered illusion. It relies on an architecture called Remote Procedure Call, or RPC. RPC is designed to hide the underlying mechanics of a network. It allows an application to execute code on a distant machine as if that code were sitting in local memory. The illusion starts at the client stub. When the developer calls a remote function, this local piece of code intervenes. It gathers the requested parameters and compresses them into a structured, transportable format. This process is called marshalling. The local function call is now a serialized network payload, ready to travel. To cross the physical network, that payload needs a transport protocol. The system must choose a path. It can wrap the data in a heavy, meticulous TCP header to guarantee ordered delivery. Or, if raw speed is the priority, it can attach a lightweight UDP header, firing the data off without waiting for a handshake. Regardless of the transport chosen, the resulting packet requires a very specific set of coordinates to reach its target. Inside the header are two critical 16-bit fields: the source port, indicating where the packet came from, and the destination port, indicating exactly where it needs to go. The developer never sees these headers, but the operating system routing the traffic operates entirely on these numbers. An IP address gets the data to the correct physical machine, but without a specific destination port, the server has no idea which running application is supposed to receive the payload. Think of a server as this massive commercial building. The IP address brings the network packet to the front curb. But inside, there are up to 65,535 individual doors, each representing a logical communication port. The packet must know which door to knock on. The first tier of these doors, ranging from 0 to 1023, are the well-known ports. They are permanent, standardized locations. A web request knows to go to port 80 or 443. An email uses port 25. The next tier, the registered ports, up to 49,151, are also generally static, assigned to specific databases and established services. The final tier of doors, numbering 49,152 to 65,535, operates entirely differently. This is the dynamic or ephemeral port range. These doors do not belong to anyone permanently. The operating system assigns them on a temporary, on-demand basis to sessions that need a quick, short-lived connection. This diagram illustrates the core routing conflict of RPC. By default, RPC services do not use static ports. They live in the dynamic range. Every time an RPC service starts, the operating system assigns it a completely random port number from that ephemeral block. If the destination changes every time the server boots, standard network routing fails. The incoming packet arrives at the server carrying an RPC payload, but it lacks the exact door number. Without a known address, the data is stranded. To resolve this architectural blind spot, the operating system employs a dedicated meta service. As soon as it receives that random 5-digit number, the service immediately contacts the endpoint mapper and logs its location in this internal registry. To identify itself, the service uses a UUID, a universally unique identifier. This is a 128-bit hard-coded label assigned to the remote service when it was first programmed. The client application knows exactly which UUID it wants to talk to. It simply needs to know which door that UUID is currently hiding behind. Port 135 provides the critical anchor point. By keeping an active, real-time map of UUIDs to dynamic ports, the endpoint mapper takes a chaotic, shifting environment and makes it continuously navigable.
The actual connection process happens in two distinct steps. First, the client initiates a query across the network directly to port 135. It presents the UUID of the service it needs, asking the endpoint mapper for the current location. The endpoint mapper checks its registry, finds the matching UUID, and sends the corresponding dynamic port number back to the client. With the discovery complete, the client severs the connection to port 135. It immediately spins up a completely new direct connection, this time aimed squarely at the newly discovered dynamic port, where the RPC service is actively listening. The payload arrives. On the receiving end, the server stub, also known as the skeleton, takes over. It unmarshals the network packet, extracting the original parameters, and hands them off to the local server application. The server executes the function. It calculates the requested data, packages the final result into a reverse payload, and sends it back across that same dynamic connection to the waiting client. This intricate two-step routing sequence happens in milliseconds. The developer writes one line of code, and the underlying architecture handles the registry lookup, the port assignment, and the payload delivery, preserving the illusion of local execution. While this dynamic allocation solves the routing problem, it creates a severe friction point for network security. Firewalls operate on strict, predictable rules. They are designed to inspect static ports, making a system that constantly changes its destination an inherent security risk. The vulnerability starts at the anchor. If a perimeter firewall blocks port 135, the client cannot query the endpoint mapper. The dynamic port is never discovered, and the entire RPC communication chain breaks before a single byte of application data is sent. But allowing port 135 is only half the battle. Because the secondary connection could land anywhere in the ephemeral range, administrators historically had to write a firewall rule leaving ports 49,152 through 65,535 completely open. This creates a massive attack surface. Modern enterprise networks mitigate this exposure. Administrators can configure servers to restrict RPC assignments to a narrow, tightly controlled block of ports. Alternatively, they deploy stateful inspection firewalls, systems smart enough to dynamically open a single corresponding port just long enough for the connection to succeed. The engineering elegance of a flexible, dynamic system inherently conflicts with the rigid requirements of network security. Managing RPC requires balancing automatic routing with careful, complex firewall configurations. The advantages of this architecture are substantial. By relying on the OS to hand out dynamic ports, RPC entirely avoids port collisions. Multiple services can boot up and run on the same server without tripping over each other, and developers never have to manually map out network topologies. The cost of that flexibility is latency. Executing an RPC call requires 2 full network round trips to establish a connection. Furthermore, concentrating all discovery onto a single registry makes port 135 a critical bottleneck and a highly targeted point of failure. Despite these trade-offs, this mechanism is the bedrock of modern enterprise computing. Active Directory relies on it to replicate data across domains. Microsoft Exchange Server uses it for mail client connections, and the distributed component object model operates entirely on this dynamic port architecture. The scale of this process is difficult to overstate. Every login attempt, group policy update, and administrative ping relies on this framework. Millions of times a second across the globe, clients are querying endpoint mappers to find shifting targets. A developer types a command, and the screen updates. But beneath that simple interaction is an intricate physical routing sequence, wrapping data in headers, negotiating with registries, and connecting to temporary addresses. The flexibility of global enterprise networks relies on managing constant motion, and that motion is organized, tracked, and directed entirely by the invisible doorman standing quietly at port 135.